Okay, all right. Good morning and happy Friday. We'll take a look. I think we left off on Wednesday, and I just kind of said, oh, there's one more root finding method. It's bisection method, and so we'll take a look at bisection method. Again, that's a root finding method. So we started introducing these different numeric methods that will allow us to find the roots of a function, and we have one more, and this is bisection method. Bisection method, one of the simplest kind of numeric methods for root finding, and one of the great things about bisection method is that it almost always works. Okay, it's just that convergence is a little bit slow, but it uses root bracketing. Basically, it finds an interval where it says, yeah, you know what, we know the root's got to be somewhere in here, and we just kind of keep shrinking and shrinking that interval smaller and smaller and smaller until we say, yeah, I'm pretty sure the root's got to be in between here and here, or not pretty sure, I'm sure that the root is in between here and here. And in bisection method, every iteration, the width of your interval is cut in half, which is pretty good, okay, pretty good. And so the way we start is you just need to have a left-hand side and a right-hand side. And the left-hand side has to be one sign. If it's negative, then the right-hand side has to be the opposite sign. It's got to be positive, all right? Or, left-hand side is positive and right-hand side is negative. And either of those works, and if you know your function is continuous and one side is negative and one side is positive, then you know the function has to cross 0 somewhere in there, okay? And so a convenient way to kind of check is you evaluate your function at the left-hand side, evaluate the function at the right-hand side, and the product of those two numbers has to be less than 0. And if the product of those two numbers is less than 0, then the root is somewhere, there is a root somewhere in between the left and right-hand side, okay? And we'll just kind of keep shrinking this until the difference between the left and right side, if that falls to be less than some tolerance value, some arbitrary epsilon, then we say, hey, this interval is small enough for us to kind of quit, and we'll take that root there. So this is our algorithm. You pick a left-hand side, pick a right-hand side, make sure that they have opposite signs. And then you'll just kind of repeat. If the difference between your left and right hand side is less than the tolerance level, then we'll quit. Otherwise, what we will do is we will compute the midpoint. Okay, just take the midpoint of the left and right hand side. And if that happens to be a root, then quit. That will be your root. Otherwise, what you'll do is you'll evaluate the function at the left side, evaluate the function at the midpoint, and then you ask, does the left-hand side and the midpoint have opposite signs? And if they do, then the root has to be between the left-hand side and the midpoint, okay? But if the left-hand side and midpoint have the same sign, so that this product is going to be greater than 0, then that means the root has to be between the midpoint and the right-hand side, okay? And so if the root is between the left-hand side and the midpoint, then you will take the midpoint and make that the new right-hand side. And if the root is between the midpoint and the right-hand side, then you'll take the midpoint and assign it to be the left-hand side. And then you just repeat over and over and over again, right? And then you'll see that at every iteration, the root is somewhere in between the left and right side, and in every iteration, the width of our interval is cut in half. So here we will do it. This is the function we've been trying out, log of x minus e to the negative x. And I'm going to just start off at two arbitrary values, 1 and 2. Okay, and we know the function at 1 is negative, the function at 2 is positive. I can just kind of check, all right? So, and I'll also specify my tolerance level will quit when the difference between the left and right hand side is less than 10 to the minus 8. So I'll take, what is the function at the left-hand side? That's going to be FL. What is the function at the right-hand side? That is FR. Left times right, is that less than 0? Yep, that is they have opposite signs. And so this is the algorithm. It's a while loop. While the right minus the left is greater than the tolerance, just keep running this forever. Calculate the midpoint. Midpoint is L plus, x at the L, x plus R divided by 2. Calculate the function at the midpoint. And if the midpoint is 0, then we'll quit. If it's otherwise, we'll keep going. If the left times the midpoint is less than 0, then replace the right-hand side with the midpoint. Otherwise, replace the left-hand side with the midpoint. And then we'll add 1 to my number of iterations. And this while loop will just keep running over and over and over again, okay? And so eventually it stops. Then I say, all right, what's the midpoint of my left and right-hand side? And it says our number is 1.3098. And we go, okay, that sounds good. How many iterations did it take? It took us 24 iterations to reach this point. Okay, I think that's if you compare it to, say, Newton-Raphson method, which we looked at on Wednesday, I think Newton-Raphson only took like 4 iterations. I think fixed point, one of our fixed point methods took maybe like 14 iterations. I don't know. I don't remember did it have the same tolerance level? But anyway, it took us 24 iterations, which is, I don't know if you say that's a lot or a few iterations. And it hardly takes our computer any time to do 24 of these iterations. But I guess depending on what situation you're in, maybe you want it to converge faster. But again, bisection method, this is one of the few things where we can have a guarantee. Right? We can say if it's continuous and you have a left-hand side that's negative and right-hand side that's positive, or left-hand, if you have opposite signs on your left and right-hand side, we can guarantee that we will find a root somewhere in there. And that can't be said about any of the other methods, right? Newton-Raphson method, there's no guarantees there. Only that if it's well-behaved and you're close enough. But how do you know if you're close enough? But this is bisection method. Here's kind of a picture. We start off at 1 and 2. That's my left and right-hand side. And then I evaluate the midpoint at 1.5. And we can see, the left-hand side is negative, right-hand side is positive. The midpoint is positive. And so we're going to keep the left-hand side and the midpoint. And we'll throw away the right-hand side. And so that's grayed out over here. And then so at the next iteration, I'm going to calculate the midpoint of 1 and 1.5. So that's going to be like 1.25 right around here. And then what is the sign at 1.25? It's negative. And so we will keep the midpoint, and this is now the right-hand side. So we're going to throw everything away to the left of, say, 1.25. So we're going to calculate the midpoint there, and we'll throw away everything to the left. And so now here I have this and this. The midpoint between 1.25 and 1.5, somewhere around here. It's going to be like right here, okay? That's going to be my midpoint. The midpoint is a positive value, so we will throw away everything to the right. We'll throw away the midpoint to the right. So we'll take the midpoint, throw away the stuff to the right, and so this is that. Okay. At the next interval, next thing, I split this in half, and I calculate. Okay, what is the value of the function at the midpoint? And it's a little bit tough to see because it almost looks like the midpoint's right in the middle, or right at the root. But I think when you calculate the midpoint, it's just a little bit positive, and so we'll end up throwing away the right-hand side. And you can kind of, if I zoom in here, you can see, yeah, I guess the function, because the function goes straight through the middle of this blue line, you can see, okay, that's going to be just a tiny bit positive. And so anyway, that is, how do I zoom out just a little bit there? Okay, so we'll keep going. All right, and so now I'm going to take the left-hand side, find the midpoint, and we're going to throw away the left-hand side. We'll find the midpoint, and I think we throw away the left-hand side again, and so we just kind of this keeps shrinking. We could see this is after a few iterations. This is what we get, and we would just kind of keep going and going and going. This is bisection method here. Okay. One strategy is you can use root bracketing methods to get close to a root. Okay. And then once you do so, once you get to like this point, you could say, hey, you know what, the function in here is almost linear. So rather than keep going through this process of like cutting it in half and cutting it in half and cutting it in half, where, you know, in the beginning, cutting it in half, like you're cutting off huge chunks, right? But then at this point, cutting it in half, you're just like shaving off tiny little things, and you're only improving your accuracy a little bit. So at this point, but you know, right here, this, if we zoomed in again, we could say like, this looks pretty linear, right? Like when you zoom in, it looks pretty linear. So Newton-Raphson method like should behave pretty well. And if we start here and we say, hey, let's use Newton-Raphson method to find the tangent line at this point and find the thing, like that's going to get us pretty close. So so once you get close to a root, you switch over to Newton-Raphson method or secant method or whatever, and then it'll converge really fast. So you do like the first, I don't know, however many iterations as bisection method, and then switch over to Newton-Raphson, and then get, you know, the advantages of quick convergence there after you you know, safely get close enough, because Newton-Raphson says, hey, this will work if you're close enough to the root, but the problem is if you don't start off close enough to the root, you know, we saw some of the animations where it just went all over the place. Okay. We can talk about order of convergence as far as like the performance of these things, and basically as you have some kind of, you know, we're looking at how much does the error shrink with each iteration. Okay, how much does error shrink with each iteration? And so for bisection method, with each iteration, the amount of error we can see very clearly gets cut in half. All right, and so every iteration, the next iteration, the amount of error is cut in half. And so that we would say the order of convergence though is 1. This is linear convergence. Okay, we're cutting it in half. And it says it can be shown that, so we're not going to show it. We're going to kind of skip over the math here. Again, if you were to take the math course, numeric methods, you'd do all of this kind of mathy stuff that talks about orders of convergence for these things. But we're just going to skip that and just say, hey, you know what, when you have Newton-Raphson, you get this second order quadratic convergence, just basically saying it converges much faster. Newton-Raphson converges much faster. Secant method, its speed of convergence is somewhere in between, around 1.6. So not as slow as linear convergence, not as fast as Newton-Raphson's quadratic convergence. Order of convergence, something somewhere in between. Again, we're skipping all of that math stuff. We're just going to say, hey, these different algorithms, they converge at different speeds. Again, Newton-Raphson, we love Newton-Raphson because it converges quickly, but it doesn't always converge. That's the thing. So what do we do? So that's what we have there. Okay, let me give you your first view quiz answer. First view quiz answer is the letter D. D as in dog. D as in dog. Okay, let me talk about derivative approximation. So Newton-Raphson method, we said, hey, we love Newton-Raphson method. It's good for finding roots. It's good at converging very quickly to the thing. And the way it finds its next value is you say you take your current value, evaluate your function at the current value, divide by the slope of the function at the current value. That will give you, so if you remember, I don't know if I have it. All right, so in Wednesday's slides, we said, you know, you have this right triangle. Okay, so if we so you have this right triangle, and we say, all right, if you start off here, you know, the value of the function is right here. That's your rise, and then to kind of get the length of the run, you do rise divided by the slope, right? Because slope is rise over run, so you swap the run and the slope, And then to get the length of this part, you do rise divided by slope, and the slope requires you to calculate basically the derivative at that point. So so that's where we are here. We calculate the value of the function, which is our rise, calculate divide by f prime, which is our slope. So this requires us to figure out, hey, what is the slope? What is the derivative of the function at xn? Okay, and so that's what we did. Right. So we requires finding the derivative at the point xn. We might choose to write a function that calculates the derivative. And so when we were doing our example function of log of x minus e to the negative x, then the derivative is 1 over x plus e to the negative x. Okay, and we found this using calculus. And when we did that, we can punch in some number, and we can say, all right, the value of the function is 1.6, and the value of the derivative, f prime of 5, is 0.2067379, right? And here I just have the function 1 over x plus e to the negative x. That's my f prime function. And here is the function at 5. Here is this the tangent line with the derivative there, shown in the red dotted line. Okay, and we go, okay, great. That's how we find we found the derivative analytically using calculus. Okay, but sometimes we say, well, I can't figure out the derivative here, right? So sometimes you're in a situation where doing the calculus to get your derivative, for whatever reason, is hard. Okay, so you might be in a situation where the function it behaves a little bit weird, or something's weird about it, and figuring out the derivative is just something you can't be bothered with. So what do we do? Well, we can try to approximate the derivative. So that's what we'll do. We'll approximate the derivative numerically. And so if you remember, what is the definition of a derivative? So in calculus, your first week is probably on limits or something like that, and then after you learn limits, you say, all right, then we'll talk about the derivative, and the derivative is defined in terms of limits, oftentimes, I think. And so you say, okay, if you want to find the derivative of the function at a, you do a plus this little h, and you say, how much did the function change between f of a and f of a plus h? And then you divide by h, and you say, hey, just try to get h to 0. Take the limit as h goes to 0, and that will be your derivative. That's the definition of the derivative. And so to approximate the derivative, we're going to say, well, we're not going to push h to 0, but we'll just take a small h, like 10 to the minus 6 or 10 to the minus 5 or whatever it is, right? Just plug in a tiny little h, and then we can do the calculations and see how much it changes, right? So here I'm going to say this is f prime approximation. My function, f of x, is log of x minus e to the negative x. And here I'm going to just say h is going to be 10 to the minus 6. And so I'm going to do, I calculate f of x, and then I calculate f of x plus h, which is just going to be log of, I do x plus h, minus e to the negative x plus h. I just do that. And then I say, all right, what is the difference between f of x plus h minus f of x, and divide by h? So this is going to be the value that the function returns. And I say, hey, print this out, calculate the approximate derivative at 5, and give me 12 digits. And when I do this, I get 0.2067379236669. How does that compare to the quote-unquote true value? So remember, f prime, we used calculus, and we said, oh, f prime is going to be 1 over x plus e to the negative x, right? So when I do that, the computer says I get 0.20673794699, right? And so we can see we are accurate up to 0.2067379. I'm accurate to 7 places, and these last 5 digits, 23669, are different from these last digits, right? The first 7 digits, 0.2067379, are the same, but these ones are off. Okay, and we go, hey, I think that's reasonable. We got 7 digits of accuracy after the decimal place. I think most of us would say, hey, that's pretty close. Okay, I think, right? And so we'd say, okay, pretty close, not exactly the same. Sure, we have a 4699 over here, we have a 236 over here, not exactly the same, but pretty good. The way we calculated it was we did x plus h, all right, and my h is a positive value of 10 to the minus 6. What if I have a negative h, right? So basically, the previous one, I'm approaching h goes to 0 from the right-hand side. What if I approach h goes to 0 from the left-hand side? Okay, how is this going to change? All right, so here I have f prime approximate negative is the name of my function, and it's the exact same function. The only thing I've done is I've made my h a negative value of negative 10 to the minus 6. Okay, and if I do that, again, my value is very close, but let's just kind of compare what it looks like to the true value. So remember, the true value is 0.2067379469999. Over here, say 7 digits of accuracy. The last digits, so after the 9, I get a 46. Over here, I get a 70. Okay, that's from the negative side, and then from the right hand side, I end up with a 23. Okay, so the left hand side is just a touch too big. After the 9, I get a 7. Okay, the right hand side is just a touch too small. After the 9, I get a 2. Whereas the true value after the 9, I get a 4. Okay, so and that's because there's a little bit of curvature in the function. And so when you come in from the left hand side, your slope's a little bit too steep, and when you come in from the right hand side, your slope's a little bit too slow, or too small. Okay, and so we can try to correct for this by calculating both the left and right hand side. So this is an exaggerated illustration. Okay, so here's the function in blue. There's curvature. You can kind of see some of the curvature in blue. The true derivative, or true slope, is the red dotted line. Okay, and then and here I'm using a very big h of +1 or -1, and so the left-hand side derivative is shown in orange. Okay, and you can see, I draw it through here and here, and the slope of the orange line is too steep. Okay, and then the right-hand side derivative, which is shown in green, is too shallow in green. So what I'm going to do is I'm going to try to basically try to average the two, okay? And we're going to get basically something along close to the dotted line. That's kind of the idea here. And so my balanced approximation is I'm going to take my h, and I'm going to calculate f of x plus h, and then I'm going to also calculate f of x minus h, right? So I'm going to do log of x plus h minus e to the negative x plus h, and then I'm going to do log of x minus h minus e to the negative x minus h, and I'll take the difference between the plus and the minus. And so now the distance between these two things is 2h, so I'm going to divide by 2h here. And if I do that, I get a pretty good number. Okay, so remember, the other one was accurate up to 7 places, 2067379, and this one I think is accurate up to 10, 2067379 469, the last two digits 84. Okay, here I get 0.2067379 46999. So that, just doing this, one small trick, now I've gotten three additional decimal places of accuracy. Okay, our performance isn't always going to be this great, but I get this approximate derivative by just doing a little x plus h and an x minus h, taking that, and now I think I get a pretty good derivative approximation there. Okay, And that's that. And I can generalize this to any kind of function here. Okay, so it doesn't always have to be this log of x minus e to the negative x. It could be whatever we want. I just need to just make up some arbitrary function here, okay? And then we're going to calculate the derivative of the function at x. And here I just have this arbitrary h value. We can adjust this to be bigger or smaller as needed. And then I'm going to just say, hey, what is my left-hand side? That's going to be x minus h. What is my right-hand side? That's going to be x plus h. And then whatever function we have here, we're going to calculate the function at the right-hand side minus the function at the left-hand side divided by 2 times h. And that's going to be my derivative approximation. Yeah, question?
Is there any way we can guarantee like a certain amount of precision at any point in that function?
There is no way for us to guarantee a certain amount of precision without knowing what the function is and without knowing at what point you want to calculate your thing, right? So because and the reason why we can't is because we're dealing with floating point numbers. So if we were dealing with real numbers, if we and from a theoretic standpoint, it is impossible to design a computer that can work with real numbers. Computers will always be working with floating point numbers because real numbers require infinitely many places, right? Like you'll never be able to have a computer that can store pi perfectly. So we're always going to be working with floating point numbers, and because of that, the amount of precision we have is going to be different when we're close to 0 versus when we're close to 1 versus when we're working with like a billion, because the number of decimal places like kind of slides around with that. So unfortunately we can't guarantee anything. Yeah, but so we'll talk about this in a little bit. But this is just a general thing. This is I will tell you, this is a good piece of code to just have in your back pocket. Okay, if you need to approximate a derivative, this is going to get the job done in most cases. Okay, if you have a continuous function, all right, and you know that you're not going to be running into some kind of weird thing where as long as these things don't like evaluate to infinity, right? Like if you have like tangent and you're plugging in something where you're going to get like tangent of 90 degrees, then sure, that's going to break. But as long as you're not running into a situation like that, this is going to give you a pretty good derivative approximation. Okay, you just take your x, add a little h, take your x minus a little h, calculate the difference between that, divide by 2h, and you're going to get something good. So here, if I just plug in, my same arbitrary function, log of x minus e to the negative x, this is my derivative approximation. We say, hey, that's pretty good. Okay, here I made another one. Let's just do x squared. This is a very simple function that we understand. What is the derivative of x squared at 5? Okay, well, the derivative of x squared is 2x. I plug in 5, I would get 10. And this is my derivative approximation. The derivative approximation says, yep, 10. We can say, is it really 10? And we can ask it to print out a bunch of digits. And the computer says, okay, it's not really 10. I have 10.00000000014. So I think we're accurate to what? 1, 2, 3, 4, 5, 6, 7, 8. So 8 places after the decimal, it's pretty accurate. It's not exact. The theoretic value is 10. Derivative at 5 is equal to 10, theoretic value. And our floating point approximation is a little bit off. Okay, a little bit off. But for most intents and purposes, I'd say it's pretty good. Here, we used h equal to 10 to the minus 6. And you might be like, well, what is our definition of the derivative? The definition of the derivative is as h goes to 0. So why wouldn't I just shrink my h to be something even smaller? Why don't I just use 10 to the minus 7, 10 to the minus 8, 10 to the minus 10? Okay, why don't I just do that? Okay, we skipped over some of these slides on the floating point section. The last few slides was on this thing called catastrophic cancellation. Okay, But, or I mean, I think I just gave a very short description about, like, you know, measuring a plank of wood and stuff like that. But this is an issue. We are calculating a difference. Anytime you calculate a difference using floating point numbers, you do a subtraction operation, you run the risk of catastrophic cancellation, and we run into that problem here. And so here I'm going to ask the computer, please approximate the derivative of our function, which is x squared. Please approximate our derivative using different values of h. Okay, so we say, hey, let's plug in, you know, we're going to plug in 5, we're going to add h, we're going to plug in 5, subtract off h, we'll square that value, and we'll see how much these things change. And again, the question is, why not just shrink h to be as small as possible? Because in theoretically, it is as h goes to 0. So you might say, well, why are we using 10 to the minus 6? Why don't I use something even smaller? But again, the computer is not handling real numbers. They're using floating point numbers. And with floating point numbers, you only get a certain amount of precision, and we start running into problems. And so here, if I do 10 to the minus 5, I get 9.999. It's pretty close to 10. And then these last few digits are off, okay? 621423. So I'm off by, you know, 0.0000000038, something around there. Here, my last digits are 139 at 10 to the minus 6. And if I say, hey, let's do 10 to the minus 7, we notice I'm off by a lot more, okay? I lose accuracy, okay? I go from here to point, you know, something. I lose an entire kind of decimal place of precision, okay? If I shrink it even further, 10 to the minus 8, it gets even, I'm even more off, okay? And at 10 to the minus 10, I'm more off. 10 to the minus 12. Now I only have 10.000, okay? I'm only accurate up to like 3 places after the decimal, okay? And at 10 to the minus 14, I'm not even at 10, I'm at 9.769, okay? And then at 10 to the minus 15, I get 8.88, and then at 10 to the minus 16, my derivative approximation is 0, okay? What happened here? How did I end up getting 0, right? So our machine epsilon is 2 to the negative 52, right? So machine epsilon is, what is the smallest number you can add to 1 where you get a number where the computer recognizes that it's not the same, okay? It's no longer 1. And that's 2 to the minus 52. It's around 10 to the minus 16, okay? But that's just when your base number is 1, okay? You can add 1. When you get to the number 2, then you can no longer add 2 to the minus 52. You have to add 2 to the minus 51 because it's floating point. So once you get to 2, the smallest thing you can add is 2 to the minus 51. Once you get to 4, the smallest thing you can add is 2 to the minus 50. Okay? And so what is 2 to the minus 50? 2 to the minus 50 is something bigger than 10 to the minus 16. 2 to the minus 50 is 8.8 times 10 to the negative 16. So this is the smallest value I can add to the number 4. So I can do 4 plus 2 to the minus 50. Whoops. And I can say this is x and y is 4. And I can say x equal y, and that's going to come back false. Okay? But if I try to add something smaller than that, so if I say z is going to be 4 plus 1e minus 16, 10 to the minus 16, okay? Here's z, and if I say is y equal to z, that comes back true, okay? So y is 4, and z is 4 plus 10 to the minus 16. It's not able to do that, okay? So here I am, I'm at 5, and if I try to do 5 plus 10 to the minus 16, the computer says that's still 5. and therefore when I do the left-hand side and the right-hand side, there's no difference there. And so it comes back and says, hey, the difference is 0. So so you have to kind of keep these things in mind. As you move up the number line, your h might have to get bigger, right? If you go high enough up on the number line, you might not be able to add 10 to the minus 6 anymore. You might have to start adding 10 to the minus 4 and 10 to the minus whatever, as your numbers get bigger and bigger and bigger. So 10 to the minus 6 works well around 5, okay? And keep in mind, our function here is what? It's x squared. So what am I doing? I'm doing 5 squared, and I'm getting something on the order of 25. So now that's between 16 and 32. And so, how much can you add to differentiate from 16 and 32? It's a bigger number there, okay? So there are limits to our derivative approximation because of the nature of the computer, the floating point numbers. Most of the time, we don't have to worry about floating point stuff, okay? Most of the time, we don't have to worry about it. But it is something that's always there, and especially when you're doing numeric methods where iteratively things get smaller and smaller and smaller and smaller, then you start running up into the limits where the number line isn't this continuous thing, but there's tiny little steps in the number line, right? These 2 to the minus 52 sized steps along the number line that you can't, that exist. Okay, so in our brief little experiment, using a value around 10 to the minus 6 is a good choice. But yeah, as you use a smaller and smaller h, the accuracy drops dramatically, and it drops down to 0 when the floating point math no longer works there. Okay. All right, let me give you your second view quiz answer, which is the letter E. E as in elephant. E is our second view quiz answer. Okay, derivative-based optimization. So now let's talk about numeric optimization. And our first kind of class of numeric optimization is just going to be based on derivatives here, okay? So a lot of things, like in machine learning, even in just basic statistics, can be turned into little optimization problems. Optimization problems are when you try to find the local min or local max of a function. So for example, linear regression. Linear regression is an optimization problem. You are trying to find the slope and the intercept of your trend line, okay? And we've defined, how do we define the best fit trend line? It's the line that minimizes what in linear regression? It minimizes your sum of squared residuals, right? So you take your trend line, you have the residuals. What's the difference between the actual value and what the trend line is? That's your residual. You square up all of the residuals, you add them up, you get your sum of squared residuals. And we said the best fitting line is the line that minimizes those sum of squared residuals. Now, that has been solved, and we know you do, the slope is what? Correlation times sy over sx and things like that. And that problem has been solved, but there's lots of other things where we say, hey, you know what, the answer that we want to get, is the solution that's going to minimize or possibly maximize something. Most of our algorithms for optimization are like minimization things. Sometimes you want to find a max, and you just use the exact same algorithm. You don't have to think of anything different. Just use the exact same algorithm. Just take your function, multiply it by -1, right? So if you want to find the top of the hill, just make it upside down, okay? Because you got a function that's always able to find the bottom of the hill, right, or bottom of the valley. So you just take your function, multiply by -1, apply your minimization thing. That's going to give you the same location. Okay. So far we've been learning all of these root finding methods, and we can easily switch from a root finding method and make it an optimization method. All we have to do is we just say, do a root finding method to the derivative, right? So if you think back to calculus, you could find local mins and local maxes by taking the derivative of a function, setting that equal to 0, and solving. And when you do that, you get your critical points, and that's going to correspond to either local min, local max, maybe a saddle point, or something like that. But overall, that's how we find. That's one way for us to find local mins and local maxes. So derivative-based optimization is just basically take any root finding algorithm and apply it to f prime. Okay, so you find the derivative of a function, and then apply any of these root finding algorithms. So the root finding, so you could take bisection method, apply it to f prime. You could take Newton-Raphson method. That's probably one of the most popular choices, just because Newton-Raphson converges so quickly. But any of the other things, fixed point iteration, secant method, any of those things will work. Okay, and then once you get your critical points, you evaluate those things to do that. Finding the derivative, you don't have to do it analytically. In the examples I'm going to show you, we're going to find the derivative analytically using calculus, but you don't have to. You can basically, when you're evaluating functions, okay, and you need to find the derivative f prime, the computer treats functions as just this little black box. You put in a number, it spits out a number, okay? How does it go from the input to the output doesn't matter to the computer. It just needs to get a value, and that's going to be the thing. But okay, let's just do Newton-Raphson method for optimization. So Newton-Raphson method is a root finding method, and we're just going to apply Newton-Raphson method to the derivative of a function. So instead of finding the roots of the function, we want to find the roots of the derivative of the function. So so instead of doing f divided by f prime to find the roots of the derivative, we're going to do f prime divided by f double prime. Okay, so we want to find the value of the derivative divided by the slope of the derivative, which is f double prime. Okay, and so this is the exact same algorithm. So if I pull up the exact same, so this is Newton-Raphson for finding roots, and basically this is finding the roots of f, and just replace f with f prime, and replace f prime with, you'll get f double prime, and that's basically what we have, what's going on here. Okay, and so you just do this, and that will get you local mins and local maxes. So if this is our function, my function is 0.25x to the fourth minus 0.5x squared. My derivative is x cubed minus x, and my second derivative is 3x squared minus 1, and we'll use that. Okay, we'll use f prime divided by f double prime. And so here's what the function looks like. We're going to find the critical points using Newton-Raphson method. We're going to find where the derivative is equal to 0. So that's going to be right here at the local min, right here at the local max, right here at the local min. And so I have f prime is x cubed minus x, and f double prime is 3x squared minus 1. And if I start off at, say, 2.1, which is going to be up here, will it find the local min? And it does. So here x old is this. My x new is take the old minus f of prime x old divided by f of prime x old, and that's going to give me x. Basically, this is x at time n, and this is going to be x at time n plus 1. And then I just run this while loop. Okay, just get the next iteration using the same thing. Okay, keep going over and over and over again. And where does it end? It ends at 1. Okay, which indeed that's a local min. Okay, if I start off at a slightly different starting point, 0.9, I also end up at 1, approximately 1. Okay, it's always approximately, right? 1.000000. This is a lot of zeros, so but I get approximately 1, so that's going to be our local min. If I start off at, say, 0.1, I get something that's approximately 0, 10 to the minus 24, approximately 0. Here, if I start off at negative 10, so way off to the left, way off in this corner over there, I end up at negative 1. And these are all just different examples of our Newton-Raphson method getting us to basically a local min or local max. And it works. Now, here I wrote these functions. F prime, you plug in x, and it's going to spit out x cubed minus x. And f double prime, you plug in an x, and it spits out 3x squared minus 1. I've put this stuff in here using calculus. But if you didn't want to be bothered with the calculus, you don't have to. You can go back and use this derivative approximation, because all it is, the computer doesn't care what this function is. It doesn't know, okay? It just says, oh, you're plugging in x old, and I need to calculate the output of some number. And whatever has to happen inside this function f prime, whether it's x cubed minus x, or whether it's x minus h, x plus h, f of function right, function left divided by 2h, the computer's just following steps and it spits out a number. And once it spits out a number, it can do calculations. So you don't have to figure out what goes inside the function using calculus. Whatever goes inside the function can be just this derivative approximation. It just needs in a number. And this is going to give us a pretty accurate number. The derivative approximation will give you, again, a pretty accurate number. And so you don't, if you can't figure out the calculus, if you can't figure out the derivative, that's okay. Just use your derivative approximation, and that's going to be good enough. And same with the f double prime. Your second derivative, you can just apply the function to itself here. You can just say, all right, I need to figure out the second derivative, okay? Well, just take your derivative approximation function, plug it in here, okay? And then you get, what is my derivative approximation on the right-hand side? What's my derivative approximation on the left-hand side? And then when you calculate the difference between that and you need to divide by 2h, that will give you your approximate second derivative, okay? Obviously, if you keep doing this, you'll kind of get like a growing amount of error. It's like their errors start cascading too much. But overall, it still works. And again, we're always just kind of dealing with approximations. And so we say, hey, you know what? If I'm looking for an approximate answer, I can get my approximate derivative. I can get my approximate second derivative. And I can get my approximate root, and we're okay with that. When we say, hey, I want to do a numeric method, we're saying I'm okay with approximations. Again, in our class, we're not covering all of the nitty-gritty in terms of like convergence and all of that orders and stuff. That's, if you take the formal class on numeric methods, that's like the stuff that you have to kind of dig through and cut through. This is just kind of like, here are the methods, they work, and they are useful tools to have, because a lot of times the math gets hard. So anyway, that's that. It works. We'll look at more optimization methods next week. Let me give you your last view quiz answer, which is the letter A. A as an apple is your last view quiz answer. Okay, we'll end here. Have a great weekend. We'll see you on Monday.